Hey, this is Doust here. I'm going to do an answer key for the balancing chemical equations assignment. Since some of you had questions, I want to make sure everyone can be successful here. So starting off at the website, the fet.colorado.edu, balancing chemical equations, I'm just going to click on the intro. Now I can see here on the Make Ammonia screen, ammonia is NH3. That's probably the most important fertilizer in the world. It allows us to grow a lot more plants than we normally could, feed a lot more people than traditional methods allowed. And so, if I start off with N2 and H2, they can do a chemical reaction and rearrange to make NH3. But if you're looking at the number of atoms on the left-hand side, remember those are called the reactants, and the right-hand side is the product, you can see that these things do not match up. I've got two of the blues, that's nitrogen, on the left, and only one on the right. Atoms just don't disappear like that. I've got two hydrogens on the left, three on the right. Atoms don't just get created like that. If I want to come up here to the top, we can see here there's two different scales, old-fashioned scales. And you can see two on the left, one on the right, versus 2 and 3. Either way, these atoms don't match up. But if I say, well, what if I made 2 ammonias at the end? Then I could have my nitrogens equaling each other. Now, I have 6 hydrogens at the end. I can't end up with 6 if I started out with 2, but if I add more hydrogens there, I can get the N's and the H's on each side to be equal. So that might seem a little weird for us because why did I add more hydrogens at the beginning? What I'm trying to do really is figure out what's the ratio of how many N2s and H2s do I have at the beginning to get how many NH3s at the end. And so it's kind of a guess and check. If I had 2 of those and 3 of those, I could wind up with 2 of these. And the numbers of nitrogens and hydrogens on each side are the same, before and after. Oh, you could take a screenshot here of this part and that part, copy it over for question number 2. This purpose of the balance scales and bar charts and simulations allow us to visually see what's happening here. If we went to the bar chart, you can see here 2 on the left, 2 on the right, 6 on the left, 6 on the right. This allows us to keep track of the number of atoms on each side. Question number 4. In order for the chemical equation to be properly balanced, the number of atoms of each element needs to be the same before and after. Not balanced because 2 doesn't equal 1 and 6 doesn't equal 3. Yes, balanced because it's 2 and 2, 6 and 6. So let's go over and separate water. If you run electricity through water, you can break it up into hydrogen gas and oxygen gas. And if I had 1 molecule of water at the beginning, I couldn't just make 1 molecule of hydrogen and 1 molecule of oxygen at the end. The hydrogens are actually good at the beginning. You can see here that I have 2 at the beginning, 2 at the end, but my oxygens don't match up. If I add another molecule of water, now I've got 2 and 2. My oxygens are equal. My hydrogens are no longer equal, but what do? I change that coefficient there. So the balanced chemical equation is when I have 2 molecules of water, that is 4 hydrogen atoms and 2 oxygen atoms as reactants, and then I make 2 molecules of hydrogen gas, H2, and 1 molecule of oxygen gas. So So at the end, I still have 4 atoms of hydrogen and 2 atoms of oxygen. Switching back over here to our scales, you see 4, 4, 2, 2. If I didn't have this, they wouldn't both be equal to each other. A similar kind of thing for question 6, 7, 8. I can copy over my coefficients right here, the 2 waters, and then 2 hydrogen gases, these H2s, 1 oxygen gas, O2, and I can take a screenshot of this part here. You just need to do this part and this part there. We don't need to copy over a ton of stuff. Going down to combusting methane, it's going to be a similar idea. Methane, CH4, that's the natural gas, say if you had a gas stove, burns with oxygen in the air. Combustion reactions make carbon dioxide and water. If we take a look here, we can see there's 3 different elements we're keeping track of. There's the C, there's the H, and there's the O. And the scale with the carbon atoms is level. It's 1 and 1 before and after. So that's fine. I see my hydrogens though. I started off with 4 atoms at the beginning, 1 CH4. I need to have more hydrogens at the end. They couldn't have disappeared, so I'd go like that. Cool. So now my carbons are good, my hydrogens are good. The only thing that's not good is the oxygens. If I have 4 atoms of oxygen at the end, that 4 right there, I need to have 4 at the beginning, like that. So now everything is equal. So that's the main part for questions 1 through 11. And then question number 12 is just a little bit of review about the difference between the coefficients and the subscripts. So it's looking at these 2 NH3s. What does the 2 tell us? Well, what do we have 2 of? 1, 2 molecules. What does this 3 tell me? It tells me each molecule has 1, 2, 3 hydrogens. Why do we change the coefficients versus changing the subscripts? Well, if we change the subscript, we're changing the molecule. If we're making ammonia, it's got to be NH3. We can't change that. So NH2, NH4 will be a completely different chemical. May or may not exist, but it wouldn't be the thing that's actually desired in the reaction. For the game here, it's kind of, turn off the sound. It's going to be a little bit of guess and check until things start to make sense to you. So I can see here, those don't look like they're equal. Because I have 2 whites on the left, 2 whites on the right, that's good. But 2 reds on the left, only 1 red on the right. Well, I want to change the number of reds on the right. Now doing that kind of messed up my whites, so I'll go back here. Okay, so now I've got 4 whites, 4 hydrogens on each side, 2 reds, that's 2 oxygens on each side. Hit check. Ooh, balance. Next. So when we're doing these, start off with 1 of each, and then make any adjustments you need to. Okay, 1 carbon on the left, 1 carbon on the right. 2 oxygens on the left, 2 oxygens on the right. Oh, that was easy. Here, okay. Start off with 1 of each. I see I've got 4 of the red phosphorus atoms here, which means I have to have 4 on the left. So the red ones are good. Now looking at the green ones, I've got 3, 6, 9, 12 in total. Here I've got 2. Now 4, 6, 8, 10, 12. 4 of the red phosphoruses and 12 of the green chlorines on each side. There you go. 1 phosphorus. So 4 atoms. Well, kind of a similar thing. We got 4 at the beginning. I need to have 4 at the end. Now I've got 3, 6, 9, 12 of the yellow fluorine atoms. So 12 on the right. I need to have 12 on the left. Now I've got 2, 4, 6, 8, 10, 12. And we just can kind of continue on going like that. Start off with 1 of each. I've got 2 H's at the beginning, so I need to have 2 H's at the end. 2 fluorines at the beginning. Oh, now I've got 2 fluorines at the end. Easy peasy. There you go. Not surprisingly, I can get 10 out of 10 the first time. If you didn't, that is okay. Just try it again. This is one of those things where you just need to keep practicing, and eventually it'll just click. It'll be super easy. But until that point, you're kind of going to be confused. But that's okay. That's what everyone goes through when they're learning this stuff. And then you can continue on with levels 2 and 3. All right, I hope this helps. And if it doesn't, let me know. We can try to figure something else out. All right.